So welcome to this webinar, which is our 20th webinar and our last one of the year. We are going to be hearing from Nigel Marriott, who is going to be presenting about the new stats guidance. And Nigel is an independent statistician based in Bath, providing consultancy and training services to non-statisticians in all industries. His career spans 30 years in many fields, but the common denominator has been his ability to demystify stats for clients who need to use stats but don't have the expertise. He is an active member of the Royal Statistical Society and blogs regularly on issues in the public domain which involves stats. So so you seem to be moving again, Nigel, from my end, which is a good sign. So if you want to just share your screen, I can hand over to you.
Okay, can you put up the share screen icon, please? Yes, here we go. So I'm sorry, I seem to be losing. I think you need to activate the share screen for me, Alison.
Well, I have to do it again. Let me just check. Yeah. Right, you should be presenter. What I'll do is I'll stop making you presenter and then.
No, here it is now. I've got it now.
Yeah. Okay.
Yeah, just 1 second. There we go. Okay, with luck, everybody is starting to see that on my screen now. Oh, sorry, on your screen. So, can you see that, Alison?
Not yet, no.
Okay, seem to have quite a slow lead. I noticed that when we were testing the sound, it seemed to be about 5–10 second round time.
Yeah.
So hopefully I won't get out of sync. But can you see that on the screen now?
It looks like other people can see it, but I can't for some reason.
Okay, yeah, so everybody can see it. So I'm getting chat box saying they can see it. Okay, I'll kick off then, if that's okay, Alison.
Okay, go for it.
Okay then, so good evening everyone, and thank you for giving your time to listen to what I have to say about this guidance document. So I'm hoping by now you will have downloaded this and read it. I've been told it's been downloaded 1,800 times. Actually, that's a month ago now, so it may well have been downloaded more. So what I want to do today is sort of just give you that overview of what's in the guidance and pull out some of the key points. Now, some of you may have been at the SOBER webinar last week, where I also presented on the guidance. Many of the slides are the same, so I'm going to try and show a couple of different things. But there's a new section at the end on, because I've got more time today, where I'm going to be talking about sampling and giving some insight into what options you have around sampling. So that I didn't present on at SOBER last week. I've got in a habit of kicking off with this little comparison that I see links between what this guidance, collect it as I'm calling it, the Pexit about the exit from Pvalues that I come on to, and then Brexit. Now, the link is this, and the fact that, first of all, the coincidence of timing. Change started coming in 2016, but there was a long history prior to 2016. So I'm not talking about Brexit at all. That's we'll leave that to one side. But P-values have been widely used in a lot of scientific research, and it's no question that contributed to development of science. But P-values have been misused. And statisticians have been aware of this, but really as a profession, we perhaps haven't done that well in terms of policing, training and teaching people, and abuses have cropped up. Now, the previous guidance written in 2008, when I read it, I saw that a textbook first-year statistics course would do it exactly that way, one-way hypothesis testing. And again, nothing wrong with that. That's absolutely what we get taught. but it left it open to being misused, and in particular being used in a bright line fashion. If your p-value is 4.9%, that would be statistically significant. If it was 5.1%, it would not be statistically significant. And that was never the way the p-values were intended to be used. So in 2016, things started to change. We had the referendum, obviously, in 2016 for Brexit, though what happened next wasn't actually that clear. Then what I'm calling PECT. We had the statement from the American Statistical Association in 2016, which was a definitive statement that was widely publicized throughout the scientific world, and I've given a link to it. What that said, though, it said what the problems were with p-values. It didn't really say what you should do instead. And the CLARE steering committee invited me to rewrite the guidance, and we met first time in November 2016. And again, the initial focus was very much on trying to rewrite the previous guidance rather than going into more depth. But then, as we got into this, we got into this big debate over what caveats should be placed on the guidance, and I'm going to come on to that. But it mainly centred around the CSM and the sampling plan. And eventually, in 2020, well, actually, the final version was written in 2019, but it took until 2020 to finish the layout and everything. The document was published, and I've just given a link there to a page that is on the blog here, which I'm just going to bring up. If you follow that link to this page here, you'll see me just giving a little bit of a personal reflection on what it involves to write this guidance. So you may find that useful to read. But the connection with what else was going on is that although the first statement by the ASA and p-values was very much about what not to do, in 2019, the ASA published a new one, which was much more about what you should be doing instead. And for me, those years, the 2016, 2019, while I was writing this guidance, I felt like I was an ambassador for the American Statistical Association as a representative statistician, in that you were one of the first industry to move into this world beyond P0.5, and therefore the guidance was written with that in mind. And there's a couple of key slides that I'm going to show you. And Brexit, we had all sorts of political shenanigans before that was settled. But the point is, we're not at the end of the process. With Brexit, you can read the news what you like about what's happening here. It's not the end of the process. There's a lot of uncertainty. Again, the ASA statement last year has given you lots of ideas. It's not just one idea, but lots of ideas on what you should be doing instead. But that means there's a lot of uncertainty about exactly what's going to happen. There's a lot of diversity of how we can go about it. And as you see with this new guidance in comparison with the previous guidance, whereas the previous one could be said to be more prescriptive about this is the way things should be done, in the new one that I've helped Claire to write, we've tried to move away from that and place much more reliance on your judgment as professionals. You're the people who are the experts in this field, and therefore, this guidance designed to support you, not replace your judgment. But that obviously opened up more uncertainty. So you can see, this is my connection between the three. They all follow similar timelines, and they've left us where we are with more uncertainty, but who knows, will potentially benefit in the way things go forward. Now, the way I would have liked to have written the guidance with the benefit of hindsight is that when the ASA published this statement in 2016, Peter Witherington, who was the person who actually introduced me to Claire, he read it, and he particularly liked this paragraph. And when I read it, I realized this was exactly what we were trying to say in the guidance. Good statistical practice as an essential component of good scientific practice emphasizes these 6 things, which are not bullet pointed in the statement as just a simple paragraph. But when you break it down, it principles of good study design and conduct, a variety of numerical and graphical summaries of data, understanding the phenomenon under study, interpretation of the results in context, complete reporting, and proper logical and quantitative understanding of what data summaries mean. No single index should substitute for scientific reasoning. And I really think that's the key thing. That's the danger of p-value. The p-value becomes the be-all and end-all of decision making, and that was never what they were intended to be. So the guidance here, and indeed statistics here, is to support you in your role, not replace your judgment. The 2019 statement, I won't read all of this, but I certainly want to highlight this point here, that we definitely want to get away from a world where p.0.51 is not statistically significant and p equals 0.49 is statistically significant. We want to get away from that. It's not black-white. And also the end paragraph here about, you know, researchers being free to communicate all their findings, glorious uncertainty. There's that word again. And the last sentence, I think, the critical one here. As statistical significance is used less, statistical thinking will be used more. And this is what my career has been about, helping people to understand statistical thinking and use it in their day-to-day life. And I hope that this guidance will be an aid to you in that respect. So let's look at some of the detailed guidance. Now, I said that with the benefit of hindsight, I would have written it much more in tune with that paragraph of the 2016 ASA statement. It wasn't written in that order, but I sort of tried to reflect the principles. But the Appendix A1 of the guidance sort of just links everything together. So I just want to emphasize what that said. So we're going to go through the 6 bullet points of this paragraph. So when we talk about principles of good study design and conduct, well, this is where all the prerequisites need to be in place before you can even use the guidance. So you need to have had a conceptual site model so that you've been able to work out where it is you need to take samples, or where it is you've got to find it easy to make a decision. You need to have selected your samples according to a proper sampling plan based on statistical principles. You need to have rules for deal with non-detect. And then you obviously need to define your critical concentration. Now, this guidance doesn't cover those points. They're assumed to be there in the first place. And if necessary, Claire may write further guidance in this field. We've certainly identified sampling plan as one possible area where further guidance may be needed. There is a lot of guidance in other industries. Sampling is something I do a lot of in my professional life. I'm currently writing a guidance for another industry body, you know, on how to take sampling in their work. So it's a field I have a lot of experience in, and so there's a lot of good sampling guidance already out there in other fields, but none of that are specifically written for your field. And I think the biggest difference with your field compared to other fields is when it comes to spatial correlation. The fact that you're selecting data that is spatially correlated not only in area but also in depth. That creates a little bit of a difference compared to other industry, but not radically so. Not radically so. So, as I say, the new guidance does not cover this. But this is where we had to spend time on the prerequisite to sort of make it clear to people that you have to do this. Otherwise, you're going to find it hard to apply this guidance here. So then you need to summarize. This was just, to me, was so critical, just making sure you plot and summarize your data. So, you know, what I'll show you later on, the dot plot and the box plot, spatial plot, summary statistics, and confidence interval. This is just basic stats, which you can present in a single page if you wish, and I'll show you the example later on. It is not exhaustive by any means. I'm not saying these are the only way to summarize data. You can summarize data other ways if you wish, but you should certainly plot and summarize your data in the first place. And then there's the confidence interval, which is the main tool to help you make a decision on whether or not the critical concentration has been breached or not. Understanding phenomenon under study. Now, I introduced something here called data type. So I basically said, well, you know, what type of data are you analysing here? And I'm going to show the examples later on. But this came up when the discussion got to the point, well, should we put in guidance about sample size? And I was saying you can't do that. It starts from the beginning with the CSM. The CSM informs the sampling plan, and the sampling plan then informs what you actually collect. So the sample size should be decided earlier. But it is true to say, however, you can still go through that process and end up with some data where everything's borderline, and you need to decide, should I take more samples? And it was that situation that motivated the introduction of data type, which I'll explain in a minute. But one thing on reflection on reading the guidance again is that the guidance perhaps doesn't make it clear enough that the data type concept only really matters when you're in a borderline scenario. If it's clear and obvious, this isn't really an issue to worry about. Good practice to get into the understanding of data type, but it's not critical unless you're in an issue of borderline case. And it absolutely does not replace the requirement to design your sampling plan in accordance with statistical principles. The then interpretation of results in context. So are the results very different from what your CSM indicated? Do you need to go back and revise the CSM? Is it a clear and obvious decision, or is it borderline, etc., etc.? And this, for me, is the true Peptic thing. You're not letting the p-value make your decision for you. You're taking the data, marrying it to a scientific judgment, and then interpreting those results in the context of what you actually need to know. Of the completing reporting, so section 6 of the guidance there had a series of statements where, you know, you need to put, basically saying to you, try and put yourself in a position where you can state that you're confident about a variety of points. And obviously that level of confidence will differ depending whether you're in a planning scenario or part 2A remediation. And then proper logical quantitative understanding what the data summary means. So this is about where we compare the confidence interval to a critical concentration, but only if you've done all the steps up to the point so far. So that's why we tried to lay out the guidance in that regard. And if it's borderline, well, we deliberately chose 3 examples in the guidance that were borderline. And that's why I say, with the benefit of hindsight, the guidance perhaps doesn't make it explicitly clear that if your decision is clear and obvious, you don't have to worry too much about what type of data you have. It does say it, but it's sort of buried away in a paragraph rather than saying that more explicitly up front. But that's why we deliberately chose 3 borderline issues, so we could pull in lots of points that you might want to consider when interpreting these data sets. And a concluding paragraph, this is very much my sentiment about what this guidance is all about, to be read and used by people with scientific training who are capable of exercising scientific judgment and wish to use that to supplement their professional judgment, not to replace it. If we achieve that state of affairs, I will certainly be very happy. So let's have a look at some charts now, and these 3 data types here. So these are the 3 data sets that appear in the guidance and used to illustrate it. But let's look at the begin what actually the kind of presentation that I put in the guidance. So we have a dot plot here, sometimes known as a histogram. It's just a variant on a histogram, where instead of having a scale down here that indicates how many samples you have within each of these numerical ranges, we're just using a single dot to denote a sample. You can see the sample size here is 19, so we've got 19 samples here, and that makes up our data set in this case. Critical concentration is 1 here. So we've got the summary statistics shown there, and then we've got the box plot here. So we have the box part here, where, you know, in we've got the lower quartile, the median, this is this horizontal line here, the upper quartile, and together that all makes the box. The mean is shown by this little brown square here, and then the stalks or whiskers, as they are sometimes known as, represent the range out to the maximum and the minimum, respectively. And so that's just another way of summarizing the data you see in this histogram, summarized into a box plot, and then you can calculate the confidence interval. And one of the things I recommended is that you use 2 confidence intervals. The intention is that the lower confidence interval, the smaller level of confidence, 95% in this particular case, is a sort of statement by you say, I'm confident that the true mean of the contaminant here is within this range, 1 to 1.4 milligram per kilogram. Well, actually, this is a scale 3. So I'm pretty confident that it's within that range. And the outer one, the higher confidence here, 99% confident, represents a range where you think, I think it's unlikely that the true mean is outside of that range. So you use a sort of smaller inner one to say I'm confident within that range, and the second one to say I'm confident it's not outside that range, leaving you this sort of in-between zone where, well, I'm not quite confident there, but equally I'm not quite confident outside, that sort of an area of uncertainty. And you can see that in this particular case, we put the bottom limits here on the critical concentration to denote, well, okay, how would I draw a conclusion here? So that's the format for data. Now, this kind of data type we call the symmetric data type. And symmetry means if I take the raw data here and split the data in half, so I've got half the data points above and half the data points below, the shape of the data that I see in the upper half here is a mirror image of what I see in the lower half. That's symmetry. And so this data set, you can see, is pretty symmetric. And it's reflected by the fact that the box plot is also pretty symmetric. The size here of the from the median to the upper quartile is roughly the same as what you see from the median to the lower quartile, and the size, excuse me, of the lower store is roughly the same as the upper store. So visually, we can look at that and say, yeah, that is symmetric data. Now, the second data set here is what we call log symmetric. So when we look at this data, looking at the dot plot, we can see clearly that is not symmetric. If I cut that in half, what I see in the lower half is not a mirror image of what I see in the upper half, and the dot plot backs that up. But if I would take the logs of these sample values, and obviously you need an undetect rule, so you can't have values of 0, then the distribution of the dot plot and the box plot of the log value will be symmetric, and that's the definition of log symmetry. And again, you can see where we place the confidence intervals in this scenario. This was the planning scenario. They are below the critical concentration, but it's still, the mean is still relatively close to the critical concentration. So I pointed out some of the issues in terms of interpreting confidence intervals in this scenario. And then the third data type would be a case of a data where it's clearly not symmetric on the actual value, and it's still not symmetric when you go to the log values. And I've set up a sort of sliding scale, but the characteristic of a fact-tailed data, you have a lot of data points here down close to 0 or very little contamination, and then you get a few sample points that are very high values. And that makes it sensitive to the number and placement of these extreme values. I'll come back to this point. But one of the effects of fact-tailed data is the fact that the confidence intervals will tend to be much wider. So those were the 3 broad data types in the data set here. Now, you might be thinking, okay, how the hell do I tell what kind of data I have here? So let me give you this little quiz here. Now, the vote button doesn't work here on this, so I'll just ask you to sort of do this in your head. But I think I know what your answer is going to be. Suppose I've got Nassim Taleb, by the way, to thank for this little exercise. He was the author of the Black Swan. So what he said was, okay, select 2 people at random from the UK, and then you're told only this information. You're told the sum of their height is 13 feet, and the sum of their net wealth of these 2 people is £20 million. You're told nothing else. That's the only information you're told. Well, which of these 2 scenarios would be more likely for height? So one person is 2 feet tall and the other one is 11 feet tall, or both are 6.5 feet. And then in scenario B, for the net wealth, one person had 20 million net wealth and the other one had 0 net wealth, or both had 10 million net wealth. So take a moment to think, what would your answer be to these two questions? So option A is when it's a big difference between the two people. Option B, two people are the same. And I don't think you would be basically saying anything different from this, that you would have given different answers. You have basically said, okay, in the case of height, both people are probably the same. They're 6.5 feet tall. And the reason you would say that is that you know that height, there is an effective maximum. Nobody over 9 feet tall has ever been born. 8 feet plus is the largest human being. So, you know, it's far more likely these are two exceptional individuals, but about 6.5 feet tall. Whereas wealth is not like that at all. There's no effective maximum. Most people don't have any net wealth, you know, taking into account mortgages and everything. So it is far more likely that one of those persons didn't have a net wealth and the other person was a multimillionaire. And therefore, height, we would say, is an example of symmetric data, whereas wealth would be an example of fat-tailed data, because there's no effective maximum. And so for me, symmetric data and fat-tailed are two ends of a spectrum. So they are not, these three data types are not distinct categories. They represent ends of a spectrum. And so this is something I've created since the, you know, you've got symmetric data at one point, fat-tailed data at another point, and log symmetric somewhere in between. One of the clues is when you look at the mean in relation to the median and the upper quartile. Symmetric data, the mean and median tend to be pretty similar. For log symmetric, it tends to be in between, and fat-tailed, they tend to be at the upper quartile or higher. That's not a cast iron rule, but it, in general, that's what I tend to see. There's a correlation with sample sizes. You can draw pretty strong conclusions with small sample sizes with symmetric, but with the fat-tailed, unless it's clear and obvious, you're probably going to need larger sample sizes. And as I said earlier, fat-tailed data is very sensitive. The mean is very sensitive to the addition of 1 or 2 extra samples. And this brings into a concept of stress testing. Excuse me. It's something I talked about in the guidance, but again, it wasn't explicitly made clear. If you take the fat-tailed, first of all, just to repeat the point I said earlier, if it's clear and obvious, you don't need to worry about data type. So this data here, you would probably say, okay, that looks like it might be fat-tailed here. Certainly this high criteria I gave you earlier of the mean being greater than the upper quartile seems to have been met there. Clearly not symmetric and everything. So yeah, you might go through all this, is this log symmetric or this fat-tailed, but is the decision clear and obvious here? Well, if your sample is a representative sample of the area you're sampling, then you know it is pretty clear and obvious that the mean is way less than a critical concentration here, and so all this issue about data type is not relevant. And even this is where stress testing come in, because one way we might sort of see this is to say, well, what if we had a couple of extra samples, say around this area here? Would that change our decision? So if I stress test that sample here, add in a couple of extreme values here, yes, the mean goes up, the confidence interval widens, hey, but it's still way below the critical concentration. That doesn't really change anything. Whereas if it's a bit more borderline, the stress testing might show, well, actually, if I did get take a couple of more samples and they were more extreme values, I may change my conclusion. And that's something you would need to take into account. Actually, there was another point I'd just like to make. Oh, yes, the other point I'd just like to make here. Actually, no, it's going to come up in the next section. So let me move on. So let's talk a bit more about sample size. So as I say, what I said so far is largely a repeat of what I said in the sober presentation, but I didn't talk much about sampling last week. So And this new guidance is not a sampling guidance. As I said, there is other guidance out there on sampling, which I'm sure can be applied, but it may be at some point the industry would like something that's written more specifically for contaminated land. Golden rule of sampling in any industry is objective, objective, objective. What on earth is it that you need to know, and what decisions and constraints need to take that into account? And that's where your CSM is so important. But saying that, you may be in a situation where you may need to say, well, okay, I'm not sure if I've taken a sample, I thought I had enough, but when the data came in, I think it's not clear enough. You know, because when you design a sample in the first place, one thing you've got to estimate the standard deviation, one of the most important statistics for determining sample size. And there's no guarantee that the actual standard deviation will be the same as what you expected it to be in the first place. So there may always be a situation where you have to ask yourself, do I have enough samples? And so there's a variety of questions you can ask yourself here. So as I say, is the answer clear and obvious, in which case you don't need extra samples. Is the mean value low to put some pre-specified level of risk? And the way it was phrased to me about your decision criteria, it was about having confidence that the risk level of risk was low relative to some pre-specification. And so there's many ways of interpreting that, but as I say, I think, you know, you might have a confidence interval that is above or below the critical concentration, but the actual mean is still not low. So I think that's something you need to think about. How sure do I need to be? The guidance talked a little bit about how to interpret confidence. Now, one of the reasons I went for two-way confidence intervals is that I've not worked in land contamination before Peter Witherington introduced me. But I have worked with scientists before, and I've worked in a food safety environment, the closest environment to this. And one thing I do know is that, you know, judgment over what is the level of risk or what is a limit can and does change as your understanding of that risk changes. And so certainly my understanding in your industry that no two experts will necessarily agree on the critical concentration. So that's one reason I went for the confidence interval, is that the critical concentration itself may be subject to uncertainty. And that brings me on to one thing that I would like to know about your contaminant, is the dose response curve. You may have some contaminant that, yes, okay, once we get up to 1 milligram per kilogram, you know, we start to get a little bit concerned. But even if it gets up to 5 or 10, it's still, the risk is still very low. It's only by the time we get to 20 or 30, it starts to become high. So, you know, the risk increases gradually. Whereas I'm sure there's other contaminants where once you get beyond a certain level, the risk increases dramatically in a very short space of time. And being able to visualize the dose response curve on the same chart, I feel would be helpful. Spatial plot. This is the guy talked about spatial plot, but there are so many different types of spatial plots, and you do need them. Fact-tailed data. The thing with the fact-tailed data is that it's the kind of data set where you get many values sampled with low or zero contamination and a few high values. And if you took a sample and you're expecting fact-tailed data and you don't have that extreme value, then to me, that's a sign you need to go back to your conceptual site model and say, well, okay, did I understand what was going on here correctly? And if you still feel that you should have some hotspot here, then that's a sign you need more samples because you didn't have an extreme value in your sample. And then stress testing, as I've talked about already. So the other thing I've learned both during the guidance and since the guidance was published is that a number of people have told me that there are, you know, you're called in to do an assessment and the client basically determines the budget for sample size, and trying to persuade the client to pay for a larger sample can be very problematic in some situations. So obviously one of the first steps to point out, if the client's not willing to pay for larger samples, then that they've got to accept the consequences that they've introduced more uncertainty. But if there really is some fundamental constraint with sample size, you can only do X number of samples, then a future guidance may be able to address these options here. So bootstrapping, Chebyshev and Bayesian. Now, Chebyshev was in the old guidance. It was used to calculate a p-value in some situation, but you can also use Chebyshev to calculate the confidence interval. It's extremely conservative. I think in some cases too conservative, but it is an option there. Bootstrapping is, I think, will give more accurate confidence intervals. And Bayesian methods I'm going to talk about, I think, are probably the most promising option here. Then it's compositing. So as I often say to people when people say, oh, client won't pay for extra samples, are they not paying for the sampling, or are they not paying for the testing? And where is the cost? If the cost is in the testing, but not necessarily in the sampling, then one solution is to take, you take a sample size of 100, but composite it up into 10 super samples for testing. This guidance does not cover compositing, but that's something that could be looked at. Incorporating the contaminant dose response curve. So instead of saying the confidence interval is for the mean concentration is within this range, instead say, based on this data, between 1 and 20 people could be at risk of some health risk or so. So the dose response curve would give you that calculation. It would be more complex, but expressing confidence interval in the form of impact on public health could be a more intuitive way to making a decision. Stress testing is also, I've talked about, it is used in a number of other industries, but there's no standardized way of doing this. So again, this could be explored in further. And then attribute sampling. So this is, instead of measuring samples on a scale, numerical scale, you measure it more pass-fail basis, or present-absent. So it could be number of samples above a threshold, number of samples below a threshold. If you do that sort of binary measurement, then that puts you in the field of attribute sampling, which in some cases can work with very small sample sizes. And I stress that some cases, not all cases. But I've got a post here on my blog, if you go to that link there, where I explored a scenario for if the government wanted to make a decision on whether or not to lift all COVID-19 restrictions. I showed that they could make that decision on a random sample of 15 people from the entire UK population. It sounds startlingly small, but the math behind it is sound in that specific situation. So so those list of options I've given you there are all around saying, well, okay, if you've got a small sample size, what could you do? Of all of these, I'm sure all of these could be used in some respect, but the Bayesian method is probably your best bet here. And here's a little example of what Bayesian thinking is about. Let's suppose you take a random sample of 20 10-year-old girls and 20 30-year-old women and tested them to see if they were pregnant, and you find that none of them are pregnant. Now, the important point here, that we've got two sample sizes of 20 with 0 pregnancy, so 0 out of 20 in both cases. Now, standard statistic would just interpret that as a sample of 20 with 0 positive for pregnancy and draw a confidence interval solely based on the data. Yet you and I would have a prior opinion. With a 10-year-old girl, to find that none of them are pregnant, well, you think, so what? I sincerely hope that is the case. In fact, if any one of them came up pregnant, you'd be incredibly shocked. Whereas amongst 30-year-old women, which is pretty much, I think, peak childbearing age for first child now is late 20s in the UK amongst women, to find that actually none of them are pregnant might be a little bit surprising there, and if I did a guesstimate that probably on average 1 or 2 should be pregnant. So the confidence interval here in classical statistics would be the same. yet you and I would draw a different conclusion because you have a prior opinion about whether or not the mean should be 0 or close to 0, or whether it would be non-zero. And the confidence intervals using the Bayesian method would be different. Now, so you could have this working in land contamination, where based on your CSM and your professional judgment, you know, a prior distribution could be specified to say, okay, I think the most likely outcome is this, and then the data either confirms that or violates that. And if it violates that, you'll have to go back and start over again. But if it confirms, then do you need more samples to confirm what your professional judgment has already said was the most likely outcome? There is a problem though with Bayesian inference, and the biggest issue is the legal system. I actually made reading a document about statistics in law a few days ago, and it reinforced something I knew was the case, that the court do not like Bayesian inference, particularly if it involves a jury trial. They've effectively banned Bayesian inference in the case of a jury trial. I'm not so sure in a civil trial. I think they may allow it in some cases. The problem here with Bayesian inference is that you can pretty much set your prior to give you the answer you want, and therefore you need to find a way of getting independent in the determination of the prior, so that you aren't just, you know, setting it to give you the answer you want. That's the basic issue with it, and from a legal perspective, there are some challenges with implementing it. So that's the point to bear in mind there. So that pretty much brings me to the end of my presentation. I hope that found that useful, and I'm ready to take some questions.
That's great. Thank you very much, Nigel. That's brilliant. I'm just going to stop the recording now.